Hello, good evening, everyone. Today is another wonderful time to have another class, and today we shall be looking at Introduction to Photovoltaics. What is photovoltaic? Photovoltaic is the technology that converts sunlight into electricity using solar cells. This process is based on photovoltaic effect, where light energy excites electron in the material, creating an electric current. Photovoltaics are usually abbreviated as PVs, and so solar cells are commonly known as PV cells. They form the basic building blocks of solar panels. We move to historical development of solar cells. Early discoveries of solar cells started between 1800 and 1950s. The first discovery of this photovoltaic effect was in 1839 by a French physicist known as Edmond Becquerel. He discovered the photovoltaic effect at just 19 years old, and he observed that certain materials generated electricity when exposed to light, laying the foundation for solar energy. And by 1873, selenium photoconductivity was discovered by Willoughby Smith, and this was a remarkable breakthrough in understanding how materials react to light. By 1883, the first true solar cell was made by Charles Friet, who happens to be an American scientist. He actually created the first solid-state solar cell using selenium coated with gold. However, the efficiency of the cell discovered was actually less than 1%, but it demonstrated that electricity could be converted directly from sunlight. And this marked the early discoveries between 1800 and 1950s. The modern era started in 1950s to 1970s, and it was marked by the discovery of the first silicon solar cell. The first practical silicon solar cell was developed at Bell's laboratory by Chapin Fuller and Persson in 1954. And this particular solar cell had 6% efficiency, which was a remarkable breakthrough at this particular point in time, making it the first solar cell capable of powering small devices. And by 1958, solar power generation was channeled to space application, and it was used in Vanguard 1 satellite, which became the first spacecraft powered by solar panels. This marked the beginning of solar energy use in space exploration. And not until 1970s, because of the energy crisis and cost reductions, solar power generation was only restricted to space exploration. But because of the energy crisis of the 70s, it was applied to terrestrial application. And the energy crisis stemmed from the oil crisis of 1973, which led a global push for alternative energy source. And government and researchers focused on lowering the cost of solar technology from then on. By 1980s, improvement in efficiency was sought for. Amorphous silicon solar cells were introduced in order to make room for cheaper solar cells. The first solar panel power plant was built in California, giving it a boost for commercial application. By 1990s, the growth of the solar energy market had increased tremendously, and the first grid-connected solar system appeared in Germany and in Japan. Government introduced solar incentives and subsidies to encourage the adoption of solar energy. And most importantly, at this time, the need to reduce the dependency on fossil fuel and the awareness of the effect of burning fossil fuel on climate change has increased, and so inducing the drive to encourage the development of solar energy market. And by 2000, the solar boom begins. So China became a major player. It became a major producer of cheap photovoltaics panels, and solar efficiency improved to over 20%, which was very remarkable, making it more competitive with traditional energy sources like power generation from fossil fuel, using coal and other forms of power generation. And large-scale solar farms were constructed worldwide. We move to the next subsection, which is generation of solar cells. Now, we'll consider, having considered the historical development of solar cells, we'll move into classifying them into generations. And solar cells have evolved over time. However, we'll classify them into three main generations based on materials, efficiency, and cost. Researchers are also developing a fourth and fifth generation with emerging technologies. However, these are not yet stable. It's still under development. So our attention shall be focused primarily on the three main generations. The first generation are generally regarded as silicon-based solar cells, which is still in operation till today. So, and it started in 1950. Remember, in the historical development that we just discussed, we said in 1954, the first true silicon solar cell that was 6% efficient was developed by Chapin et al. And it was a remarkable breakthrough. So, the most widely used type today still remains the silicon solar cell made from crystalline silicon. It can be monocrystalline and it can be polycrystalline. Efficient but costly to produce. That's something to note about silicon solar cell. Now, we have the monocrystalline silicon solar cell, we have the polycrystalline, and we have the silicon heterojunction. Now, monocrystalline are made from a single crystal of silicon, allowing for high efficiency and durability. Currently, we have monocrystalline cells that has efficiencies between 18 and 24%. However, it is more costly than the other two. Polycrystalline are made from multiple silicon fragments, and so the cost of production is actually cheaper. However, again, it is less efficient, not as efficient as the monocrystalline, and efficiency is between 15 and 20%. Whereas heterojunction silicon solar cell combines crystalline silicon with thin film layers for higher efficiency, and efficiency greater than 25% has been achieved with this technology, but the main material still remains silicon. This type of silicon solar cell belongs to the first generation. Second generation actually started in the 1980s and is still applicable till present. They are mainly regarded as thin film solar cells. They use thin layers of semiconductor material known as substrate. They are cheaper to produce, however, less efficient. Interestingly, it has its advantage in the fact that it can be made to be flexible, it can be made to be lightweight, and so you can even wear it because of its flexibility. You can place it on uneven surface, so it's suitable for portable and building integrated photovoltaics, BIPV. Now, under this category, we have about 4 types. The amorphous silicon, which is non-crystalline silicon used in small electronics such as your calculator. Some of you can see this type of panel on your calculator. Now, we don't actually need more voltage to run your calculator. So, but the beauty of it is that it is very cheap, and the cost of production is actually very cheap. So usually the efficiency is between 6 and 10%. Now, in this second generation, we have two prominent thin film solar cells that are commercially stable, and they are cheaper to produce. One of it is the cadmium telluride. It is actually cost effective and used in large scale solar farms. Cost effective in the sense that the technology for its fabrication, for its production, is far cheaper than silicon solar cell that requires very, very high temperature for its manufacture, adding to the cost of production. But in this case, the technology is far cheaper to run. And with cadmium telluride, efficiencies between 16 and 25% has been achieved. Next to cadmium telluride is copper indium gallium selenide. Sometimes sulfide is used. Now, these thin film solar cells are more efficient than cadmium telluride, and actually it has more non-toxic materials in it, unlike cadmium that is toxic. The only drawback is that indium and gallium are becoming scarce and are very expensive, becoming expensive. So the advantage in using CIGS solar cell is that it's also flexible and lightweight, and efficiency between 17 and 23% has also been achieved. Then we equally have organic PVs that uses organic molecules and flexible and printable materials for its manufacture. The efficiency is somehow low, close to that of amorphous silicon, usually between 10 and 15%. We move to the third generation, which are regarded as emerging technologies, and the quest for these emerging technologies actually started in 2000s. It focuses on higher energy and alternative materials beyond the traditional silicon. It includes the use of multi-junctions, perovskite, and quantum dot solar cell. Now, a quick look at each of these. Multi-junction stacks multiple layers of materials to capture different wavelengths of light, and usually is used for space application. Efficiency between 40 and 50% has been achieved, although the technology is actually not so cost effective. Then we have perovskite. Perovskites are made from a unique material called perovskite, offering low cost and high efficiency. Efficiency is greater than 30% and potentially 40% has been achieved. However, the stability of perovskites are still questionable. Then we have quantum dot solar cell, which uses nano-sized semiconductor particles to improve light absorption. Efficiencies between 10 and 20% has been achieved. Then we have DSSC, which is known as dye-sensitized solar cell, which mimics photosynthesis using dye molecules, and they are used in low power application. The major drawback about this particular solar cell is that the lifespan is very short. So the aging is very rapid. So, and as it ages, the efficiency declines, but very cheap. So efficiency between 7 and 14% has been achieved. The fourth generation, which are just future innovations, although research is ongoing extensively, it combines features of the third generation solar cell with nanotechnology and biological materials, focuses on making solar energy cheaper, efficient, and sustainable, which is the goal of any technology in solar energy generation, in goal of solar energy generation. So we have nanowire solar cell, which uses nanoscale wires for better light absorption, expected efficiency between 30 and 50%. We have graphene-based solar cells, which uses graphene, a highly conductive material, for improved efficiency. Expected efficiency should be greater than 25%. And we have biohybrid solar cells, uses biological molecules, e.g. photosynthetic proteins, to generate electricity. The expected efficiency is between 15 and 25%. And we have transparent solar cell, which is of advantage because we can use it readily in the construction of our window shields and any transparent interface, and it can be integrated into screens as well without blocking light. Efficiencies between 5 and 15% are expected. So a comparison of the solar cell generation: first generation, primarily crystalline silicon, efficiencies between 15 and 24%. The cost of production is very high, and applications are rooftop applications and power plant generation. This has been very successful so far. The second generation, primarily thin film solar cell, which are amorphous silicon, cadmium telluride, and copper indium gallium selenide or sulfide or sulfoselenide in some cases. And we also have, you should not forget, we have other ones like cadmium zinc tin sulfide, cadmium zinc selenide or sulfoselenide. We have others as well, but you should know this. Then the efficiency of thin film are generally between, expected efficiencies are between 6 and 23%. It's also, they are commercially available in the market today, and the cost is on the average. The cost of production is on the average, and it can also be applied to large-scale solar farms. Flexible solar panel are just achievable with second generation. Then third generation, primarily perovskite, multiple junction, quantum dots. Expected efficiencies should be greater than 30% and some up to 50%. However, the cost varies with technology, but it's way between the medium and high as well. And the good thing is this: it's good for space and advanced solar applications. The fourth generation, which are futuristic, are majorly nanowires, graphene, and biohybrid. Expected efficiency should be greater than 50%, although it's not expected to be more than 50%. So we are still in the experimental phase, and we expect that one day we'll break through with this, and we have the fourth gen commercially available in the market. So with this, we can have transparent solar cell that we can use on our windows and for so many futuristic applications, even in our cars. So generally, the application of photovoltaics can be summarized into 4 categories: residential solar panels as roof-mounted panels for home electricity, especially in small units. Commercial and industrial uses are also possible with photovoltaics. We can use it as it has been since 1950s for space exploration, and also for portable solar devices, as we commonly have in Africa, in rural areas where we don't have the national grid available. So we have it as solar chargers, calculators. We have it in our camping gears for those of us that enjoy going for camping. So then, types of photovoltaic system, which we will discuss extensively later on in our subsequent studies. Grid-tied PV systems are the first type of photovoltaic system, usually connected to the power grid and allowing users to sell excess current. So you see, you can generate electricity and make it available. You use it and also make excess available where you make money from. Then we have off-grid PV applications or systems which is independent of the grid, usually with a battery storage. Most of us have this commonly in our homes. Then we have the hybrid PV system, which combine PV with other energy sources like wind, diesel generators, and petrol generators and the likes. We'll summarize the advantage of photovoltaics with 4 major points. Number 1, they are renewable and sustainable. You see, the sun is out there available for us. It has been shining for centuries and it still promises to be shining. So, and uses solar cells, uses sunlight, which is an infinite source, unlike non-renewable energies that is bound to be exhausted with use over a period of time. Then Also, it's environmentally friendly, less impact on the environment, doesn't create impact on like burning fossil fuel, on like other sources of energy that we have currently today. Is environmentally friendly. So it's a very, very promising technology. Also, the maintenance cost, although the initial outlay is could be very expensive, but the maintenance cost is very, very cheap as compared to maintaining other, especially non-renewable sources. So it requires minimal upkeep, and energy independence reduces reliance on fossil fuels. However, it comes with its challenges as well. Number one, intermittency. The sun is not always there throughout the whole day for 24 hours. So only generates power when the sun is shining. Energy storage cost when the sun is no longer shining through the use of energy storage such as batteries for energy storage can be very expensive, especially good energy storage. Lithium energy storage is more recommended now. It's more compact to store energy better than the wet cell, deep cycle cell we used previously, but it's more expensive. Then also it requires space because solar energy farms requires extensive land area to generate electricity. So it requires large amount of land area. So thank you for listening. Till we meet again, have a wonderful time.